All right, one last thing about nuclear stability and the processes before we get into some of the kinetics that go along with nuclear decay and radioactivity, and that is binding energy. And I used that term in the last video when we talked about holding all the protons together and why there's an island of stability in the ratio of neutrons to protons. This binding energy holds the nucleus together. It's not totally understood at this point where exactly it comes from, how it works, the mechanism for it working, but we know that it exists. And so when we think about this binding energy, we can't create something from nothing, and that includes energy. That energy that's in the nucleus to hold those things together had to come from somewhere. So let's take a look at fluorine-19, the isotope fluorine-19. Now, if you get a very, very sensitive, they're called mass spectrometers, they're capable of determining the mass of small ions. And we measure the mass of fluorine-19. It's measured at 18.99840 AMUs. So one fluorine-19 atom has a mass of 18.9984 AMUs. It's not exactly 19. We tend to round it off, just like we don't include the mass of electrons and atoms and things like that. So we call it fluorine-19, but its true observed mass is 19.99840. Now let's add up the mass as if we were in UChem 1 and I asked you to calculate the number of protons and neutrons and what's the mass of this isotope. So fluorine-19 has 10 neutrons and 9 protons to make 19, correct? So 10 neutrons for every 1 neutron, the exact mass is 1.008665 AMUs. We tend to round it just to 1. And the mass of each proton is 1.007825 AMUs. We also round that to 1, and we also say that they're equal to each other, but, you know, takes the third decimal place before that's really not correct, so we just call it that for simplification of calculating stuff in UChem 1. So the true mass of these we should be able to calculate because 10 neutrons go in and 9 protons go in. So 10 neutrons has a mass of 10.08665 AMUs, and 9 protons has a mass of 9.070425 AMUs. So the mass of fluorine-19 should be 19.157080 AMUs. So now we're comparing this number and that number. So this atom, this individual atom is missing 0.15868. There's about 0.16 mass units missing from this atom. The observed mass versus the calculated mass. This mass right here is converted into binding energy. By E equals mc squared. The energy or binding energy is equal to the mass in kilograms. We have to convert that to kilograms times the speed of light squared. Very tiny masses give us large amounts of energy because 3 times 10 to the 8 squared is 9 times 10 to the 16th. So we get a lot of energy out of a very tiny amount of matter that's missing. So this amount of energy, the binding energy comes from this mass defect. It's called a mass defect, what's missing out of that calculated mass versus true mass. And the way it works is the bigger the atom is, the more binding energy is necessary because there's more protons, right? So when we take a big atom and split it into smaller ones, like might happen in a nuclear energy reactor to generate power, we're not burning up uranium and converting it directly into energy. we're taking the uranium and allowing it to undergo nuclear fission, which is splitting of the nucleus into two atoms. And when they split, each of the smaller atoms requires much less binding energy than the bigger one. So the extra energy that we recover from a nuclear reactor is really the excess binding energy. We're not burning up all of it. We're allowing it to split into smaller atoms. Each one requires less binding energy than the original. So the extra binding energy is what we're recovering to do all of our nuclear power production. So big nuclei, lots of binding energy. Small nuclei, less binding energy. But it's all about this energy defect that you can calculate. I'm not going to ask you to calculate energy defects and things like that come exam time for chapter 20. I just want you to know where that binding energy is coming from. It's coming from a difference in the calculated versus actual mass for those particular isotopes. Okay?